Hmm. Not I was thinking of using the NVIDIA software, but I don't think I can record audio. Oh, you got it?
Thank
Cool,
you.
cool. Oh, and
Okay.
classic.
Yeah.
Classic. Yeah.
Um, in the past, what I've done is we've just one person just shares their screen. We go over like notes from our professors for one or two chapters each day, and then we do some problems on our own. We do problems on our own. We go over the answers.
Vishnu, if you want to have an exam from last semester, I don't know if that's, or should I just put that on the resources?
Yeah, just put it in resources. That would have questions from all over
Mhm.
chapter one, chapter two.
True,
So
true,
as
true.
of right now, it's probably not in our best interests.
Fair, fair enough, fair enough.
So are we just going to use, yeah, are we just going to use random questions from each section?
Yeah, I mean, I have the textbook with me, so I can look at problems from the textbook. If we want, we can probably also look at homework problems. Maybe also the recommended problems from the homeworks.
Sure.
Okay. Yeah, and the textbook has a lot more than just the recommended problems, so I
So
don't think I don't think we're running short on problems. Yeah, I do get what you mean. Okay, we have a lot of people. Let's go over the notes first.
Okay.
Can anyone see my screen?
Yep.
Yeah.
Yeah.
Okay. Who's recording again? Okay. Yeah, do you have that going? Okay, I'll start. So, first section is vectors and linear combinations. This is pretty easy. Like, we've been doing a lot of this for much of the semester so far. But basically, vectors are quantities with magnitude and direction. They have components. The operations we define on them are addition and scalar multiplication. Mathematically, yeah, they're represented by magnitude and direction. Uh, they can be drawn as arrows with length and direction. In practice, it's written with an arrow over it or a bold font. So something like this. These are two different ways of writing vector f. Pretty self-explanatory. Two vectors are equal if and only if they have the same magnitude and direction, no matter where they are. They have components, 2D or 3D. They're represented by a column vector, or a n by 1 matrix. For vector addition, all you do is just add the components. Geometrically, this is represented as as forming a triangle and finding the longer side, or by forming a parallelogram and finding the diagonal. And there are some exercises here. Scalar multiplication is when you stretch or compress a vector by multiplying it by a number. And so what that means is just multiplying each component by that scalar. It scales the vector, so it's called scalar multiplication. The zero vector times any scalar is no, any vector times the constant 0 equals the zero vector. Here's some properties. The main thing to know is vector addition is associative, commutative, and distributive with scalar multiplication. And there's also the identity property. These are some problems. Linear combinations. Well, first of all, does anyone have any questions so far?
Yeah. So multiplying matrices, I'm pretty sure, is not associative, right? Like if you multiply matrix A times B, it's not the same as B times A.
Yeah.
Oh
well, no, that would be commutative. It's associative but not commutative.
Oh, right. Okay. So is multiplying two vectors commutative?
I mean, we haven't gotten to that yet, but there's two different products for vectors. What we have done so far in this class is a dot product. That product is both commutative and associative. Well, actually, associativity is undefined for it because it results in a scalar.
Right. Okay.
It's commutative though.
Yeah. Okay. Thanks.
Yeah. And if someone has any questions, please feel free to unmute yourself. I'm not looking at the chat right now, so if someone sees a question in chat, please tell me. Linear combination is when you have two vectors, each multiplied by a different scalar, and then added up with different coefficients C and D. So when you have a line, the set of all vectors of all linear combinations of one vector, you'll get a line. It will go through the origin. It'll be parallel to that vector. Did I skip something? Did I skip something?
I think so.
We went to okay. And if you have two different vectors, their linear combination will be either a line or a plane, depending on whether or not you can write one vector as the other times a scalar, which is not the case in this example.
Can I say something?
Yeah, sure.
This is like, okay, I mean, this is literally like the first question on the first example problems, but like it literally like it tripped me up just because like I was just a little bit iffy on describing linear combinations geometrically. So basically, like kind of the thing that I'm getting is if there are only two vectors to describe geometrically, it's pretty easy. Like I don't think you have to set up a system of equations. You can just look at it and see if a scalar times one vector equals the other vector. So like vector u time or vector u is equal to a scalar times vector v.
Right.
Like that's pretty easy to see. But if you have three vectors, again, it seems like pretty easy. You just set up one vector times a scalar plus the other vector times a scalar equals the third vector times no scalar. And basically you just solve that system of equations. And if you get a contradiction in your findings, like for example, on the first example problem, I got C equals 1, d equals 1 and d equals 3 over 2, which is a contradiction. So that means it would lie in all real 3D space. But that's just something that like tripped me up for like an hour straight up today. Like just like,
Yeah.
but yeah, it's pretty easy.
Yeah, I mean, we've been doing this stuff for a while now, so. Oh, right here. The geometric applications of linear combinations will give you what's called a parallelepiped, which is a three-dimensional object where each face is a parallelogram, and so each face is parallel to the other to one other, and every edge has like three other parallel edges. Something that's pretty interesting. There are a bunch of example problems. Should we do some examples, or should we go to the next section and then do examples all at once?
I think we should do examples in between every section.
Okay.
Yeah, I agree.
Yeah. So we can like then like if we put the video on YouTube, we can split it up. Just jump a section.
Okay. Do you want to do these problems on the notes, or should I do textbook problems?
Anyone's work for me.
I think a textbook problem would be, because I've looked over those notes a while, like a lot. So
Okay. Let's do textbook problems. Oh, the textbook also has worked examples. Okay.
I guess we could do like the recommended problems thing.
The recommended problems? Okay. Does anyone object? Okay. 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 Yeah, I don't have the list of recommended problems with me, so someone wants to
I got
tell
you.
me. Okay.
I'll just upload it in general for you.
Yeah, or you could tell me.
Oh, here's. I can't really tell you honestly. You kind of have to look at it. I think I don't know. Wait, these are the problem set though. Like these are all the recommended problems. Are you looking for something that wasn't in the problem set?
I'm not sure what that means.
Like I don't know if we're trying to do like problems in the section that wasn't on the recommended. Like these are all problems on the recommended problems in this PDF. So I'm trying to figure out, are we trying to do problems that aren't on these PDFs that are like just in the textbook? Okay.
Yeah. Right. The recommended problems are probably the most important ones we need to know. Cool. Let's do problem number 1. I'm gonna stop sharing for a while until I come up with a solution. Want to take? How long should we take for problem 1?
Yeah,
Yeah,
5
5
minutes.
5 minutes.
5 minutes.
Yeah.
Mhm.
Okay.
No, I finished.
Same.
Is anyone still working on it?
Okay then. Okay. So for number one, I think it's pretty easy to see they're the same vector. So the linear combinations of these two vectors will be a line. Yeah, well, at one point you're gonna have to say this is elementary. I mean, there's literally no justification for this other than the fact that it's obvious. So that point I think would be to say that if the set of all vectors of all linear combinations of two vectors is equal to the set of all linear combinations of one vector, then you have a line. So here's what I have for part C actually. Well, I'll show you what I have for part C later. But for part B, it's pretty clear that we have a plane, right? Because one vector has both a y component and a z component, while one vector has an x component. The
Can I say something?
Yeah, sure.
So okay, for B, yeah, it's pretty easy to see like okay, there's an x coordinate for one, and then the other one has a y and a z. But that might give you the false impression that like okay, well, since there's three coordinates, that might be like all real space. But like the way that they're proving it, and this goes back to answer Sid's question or comment, was basically you can prove it just by setting up an equation. So, for example, for A, we see that the second vector is just 3 times the first vector. So all we do is just set the first vector, we denote it as vector u, and then multiply it by a scalar 3. And then we set it equal to the next vector, vector v, which we just denoted it as vector v. So that's how we prove it, right? So that's the same way we can solve B. So we see that, okay, well, there is literally no scalar that we can multiply the first vector to get the second vector because there's zeros in the first vector, right? So that means it has to lie in a plane, right?
Yep. Three. Yeah.
Mhm.
Right. Yeah, you can't just say r cubed. Here's what I have for part of C actually. This is a lot more. So here you want to actually set up a system of equations. So you basically set one vector equal to the sum of the other two vectors. In this case, I'm setting vector 3 equal to a linear combination of vectors 1 and 2, with the constants being a and b, where a and b are real numbers. I then simplify this system of equations to say, to eliminate the zero terms. As was said earlier, this system of equations implies a contradiction, which means there does not exist. I should probably write this down, but there does not exist a scalar. It's going to take me a long time to write, but you basically want to say there does not exist scalars a and b such that a times vector 1 plus b times vector 2 equals vector 3. Therefore, these three vectors are linearly independent, and so the set of all linear combinations of these three vectors is R cubed. I just didn't want to get into set theory.
Are you working on MATLAB or something? I just got to this stream and I saw you were going from notes and onto this program or something.
This is actually something I made by myself.
Oh, okay. I don't know what that is because I'm not a computer science major, but it looks technical.
It's called LaTeX.
LaTeX is basically a programming language that allows you to write like formal looking functions or equations rather.
But he's just doing it for just to show us. So don't worry about it if you don't understand it.
Yeah. Don't go in. Don't look at this part. All we care about is this part.
Cool.
Yeah. Okay. Which problem do you want to do next? I don't want to draw.
Yeah, I think the drawing seems at least kind of easy. I mean,
Yeah.
like it's basically you're literally just like graphing it pretty much. And I mean, unless someone has an issue with like adding vectors together and then drawing that addition, we can work on it.
Yeah. Does anyone have any issues with geometrically representing vectors?
I think it's good. It seems.
Are those notes like from an email or something? Because I don't see those notes from my professor.
Right here, these.
Yeah, the ones you're sharing right now.
Someone sent this in the Discord. I think these are from a problem section.
Yeah, it's in general.
Oh, can we put that under notes and resources as well?
Yeah, sure. I'll upload them all.
What's this from?
These are all just from the problem section. In my problem section, this was on e-learning.
Okay. These look really nice. These are probably made using LaTeX.
Wish I had a TA like that.
Okay, 26 looks good. Yeah, let's do 26. How long should we take? Let's give it 3 minutes.
3 minutes.
Sure.
Sounds good. Yeah.
Okay.
Yep.
Okay.
Yeah.
Okay. Yeah, so you just want to set up system of equations basically. Set where the coefficients come from the scalars of the linear combination. Solve a system of equations and find the answer. It's fairly self-explanatory.
I want to say for like the linear combination stuff, like you should probably like plug back in the C and D values to like make sure they fit, because for some of them you have to check whether or not there's a C and D.
Right. Yeah. Yeah.
Yeah, definitely be sure to plug it back in to the original linear combination for C and D, because like
Yeah,
if you don't, they will go crazy and like take off points.
Yeah. For this problem, I don't think it's an issue, but it's a problem. It's something to really check for when you want to test if two or three vectors are linearly independent. But yeah, I mean, it's something you should be doing regardless of whether or not it's important. Okay. One more, or should we go to the next section?
I agree.
Yeah.
Yeah, that sounds like a good idea since I'm pretty sure a lot of people struggle with the same kind of problems.
Yeah. I mean, I'll also try to like come up with problems. Not come up with problems. Like pick a set of problems before doing it tomorrow.
But yeah, we can jump into the next section. I think this
Okay.
one's
1.2.
Mhm.
Okay. So this section introduces the dot product, which is an operation on two vectors. The domain, it will be vectors. The range will be the set of real numbers. Basically, what you're doing is taking the components of each of the vectors and multiplying them and adding the sum of the multiples. So, for example, u1 v if u's components are u1 and u2 and v's components are v1 and v2, the dot product of u and v is u1 v1 plus u2 v2. It's a commutative operation. It's commutative. It's also associative. I'm not sure if it says right here. No, wait. No, never mind. Associativity is not defined. Okay, unit vectors. A unit vector is just a vector of length 1. Length of a vector is found by taking the square root of the sum of squares of the components. Does it say here? Yeah, right here. Another thing to remember is that a vector dotted with itself will give you the magnitude of that vector squared. The unit vector in the direction of a vector v will just be v times the scalar of the reciprocal of the magnitude of that vector. In other words, v divided by the magnitude of v. And the dot product of two vectors is also represented by the product of the magnitudes of the vectors times the cosine of the short angle between them. Since the cosine is an even function, it doesn't matter which way you measure the angle. So all you need to know is that it's the shorter angle, so the acute angle between two vectors. Two vectors are orthogonal if their dot product is 0. Which means they're perpendicular. This is also extended to r cubed when two vectors are not necessarily, well, perpendicular vectors works a little differently in r cubed. So basically when the dot product is 0, they're orthogonal. The Schwarz inequality says that the magnitude of the dot product of two vectors is less than or equal to the product of their magnitudes. And this comes as a result of the fact that cosine theta is between -1 and 1. Another important inequality to know is that the magnitude of the sum of two vectors is always less than the sum of the magnitudes of the vectors. Less than or equal to the sum of magnitudes of the vectors. The dot product is distributive with a vector addition. So the dot product of vector u and the sum of vectors v and w is equal to the sum of the dot products of u and v and u and w. Direction cosines. I'm not sure if this is important, but this is something I've forgotten. The direction cosines it looks like the direction cosines of a vector are the cosines of the angles between the vector and the coordinate axes. I'm not sure how important this is. But yeah.
I'm pretty sure there is stuff on the problem section regarding that. So it'd
really?
definitely be better to like make sure you know that just in case they pick one of those questions for the test.
Yeah, I mean, it's probably good to know. Okay. Yeah. Want to go to the problems? Does anyone have any questions? Okay. Let's do them together then.
Sure.
Should we work them together, or should we work them as individuals and then talk about the answer?
I think it'd be better to do it together.
Okay.
I think so too.
Yeah, that's what I was asking. It looks like people want to do them together. I'll pick some problems. I don't know if we need to do all of them. It looks like it's pretty repetitive. Five? Okay. Let's do 5. Should we do them individually or not?
I think it's kind of hard to do problems together if there's no visual something visual to go along with it. Like it's hard to
Right.
just describe it audibly. So like unless someone has like an iPad or something that they can stream from, I think
Okay.
yeah, if you can stream on Discord while writing on it.
Isn't someone else recording? Okay. Wait, who are you? Oh, okay. No, I thought I saw someone else said they would record. Okay. What are you recording on? Your Surface? I think you can stream from your Surface, but record on your other computer.
Okay.
You could just create an alt Discord account and join from that on your Surface.
Or you could join Discord on the browser in your Surface.
Yeah. At least these chapters aren't very dense, so we have like that kind of time today.
Wait, I think I get. Wait, hold up.
No.
Okay. Oh, we can see an iPad.
Yes.
Can you switch the color?
Yeah, we can see this.
Here you can see it. Yeah, that's more readable.
Hello world.
Awesome.
Right. Yeah. Put a hat over U1 and U2. No, a hat. It's like yeah. Are you able to talk, by the way?
So, how should we collaborate on this? Square each of the terms and then take the square root of that.
And then divide it by the magnitude.
Mhm.
Yeah. Uh, do you want to go into how you found those specific numbers?
Wait, so on the last U component, shouldn't that be you had to?
Yeah, it should be you had to.
I think you can use any like combination of numbers. Well, there's only one other combination you really use where you have one, but
Okay, now I can talk. I actually think I can talk when I'm doing that. It's just I have to unmute my mic in Discord. But I actually have to go, so I can't share my screen for you guys.
Okay.
Yeah, so someone else is probably gonna have to do that, or we could just do it on ourselves and then go after it, or go over it after. It's up to you guys. But yeah,
Yeah, the second method sounds good. I mean, it worked for us before, so
Yeah, we can do this, at least for today.
okay. What problem do you want to do next? Okay. Do you want to share it? Okay, do you want to like verbally say it? Um, my laptop has a touch screen.
Or what you can do, since you said you have a Surface, you can write it on the Surface, and then we can just share the screen.
Okay. I mean, do you have OneNote? Can you share the note with someone? Is that like possible?
did you already write it down? If not, you could take a picture and send it.
Yeah, we can share it for you. I'll make one. Study room. Do you see it? It's just called study room. Yeah.
Okay. I'll screen share it. Okay. Oh, okay. I get what you're doing. Okay. Yeah, this definitely works. You set an arbitrary well, you set the components, all but one of the components, to an arbitrary value, and then you find the value of the final component such that the vector will be perpendicular or orthogonal to the other vectors, and then you find the magnitude of that vector and divide by that magnitude to find the unit vector. Yeah, that's how my TA taught it. I'm not sure how he did it, but now I remember that's how my TA taught us to do it actually. Okay.
All right. Yeah. Could you guys work that out again?
Oh, okay. So, okay. Um, I can try.
Yeah, paint.
Yeah. Okay. So this particular problem is telling us to find vectors any vector perpendicular to the vector 8 for this is too big. 1 second.
Yeah.
Okay.
I can.
Yeah. Yeah.
Uh. Okay.
Or we can
Yeah.
I can just tell you if since we already put them. So lowercase u1 was 1 in 3 over square root of 10. Yes. And for u2, it was 2 comma 1 comma 2 over 3.
2 1 2.
2 1 2 over 3. Yes.
Okay.
By the way, can you increase the thickness of your marker? Yeah, that's good. You can leave that one just like that. You
Yeah.
want.
Okay. Okay. Now we want to find capital U1. First, let's find the actual vector before we find before we find the normal vector or the unit vector. To find big U1, what we want to do is write an equation such that the dot product will be equal to 0. So we want to let's set U1 equal to x, y, and z. I'm gonna run out of room very quickly, but now we want to set the dot product equal to 0. So what was the first one? Okay, so we want to set 1 over root 10 times x plus 3 over root 10 times y equals 0. Now, the way you want to solve this is to set all components but the last one equal to 1 or equal to 2 or any arbitrary value works. But for sake of simplicity, we're going to set all but the last one equal to 1. So in this case, 1 over root 10 plus 3 over root 10 equals, times y equals 0. So then we want to solve for y. So 3 over root 10 times y equals negative 1 over root 10. Multiply both sides by root 10. So 3y equals negative 1. And so y equals negative 1/3. Is that correct? Does that sound familiar?
Yeah, that's a possible value to use because you could get like I think you can get 2 different values for y, x.
So u1 equals 1 comma negative 1/3. And so now we want to find the unit vector that corresponds with u in the direction of u. To find that, we'd have to find the magnitude, which is which is 1 plus 1/9, which is 10 over 9, which is root 10 over 3. And so then we multiply this, or we divide u1 by this. I have run out of room very quickly. Okay. U sub 1 with a hat over it equals this vector divided by this magnitude. So it's 3 comma negative 1 divided by root 10. The three canceled out because we multiplied it. Is everyone good with that? Do I need to like? It looks pretty incoherent.
It seems okay.
Okay. Should I go over the second part as well, or you two as well?
I mean, two is solved the same way, so maybe you can do another one, unless someone has a problem with this one.
Okay, let's do 6a.
All right, let's do 6a then. Do we like do it the same way as before?
No,
Just
yeah, let's do it
sure.
like that. I'll do it like this. I think I can go over it like this.
Okay, cool.
Okay, we're given two vectors, W equals W1. Oh, okay. We don't know vector W, but we're gonna represent it as W sub 1, comma W sub 2. And we're given V equals 2, 1.
To -1.
-1?
Mhm.
Okay. And so we want to describe every vector W that is perpendicular to V. Oh, this is a very similar problem. Okay. But this time we don't need to work with unit vectors. The way we would do this is, again, we'd set the dot product to equal. So W sub 1, or 2 times W sub 1, minus, because we have a negative sign here, minus W2 equals 0. Now we set all vectors but the last one equal to 1. So 2 minus W sub 2 equals 0. So W sub 2 equals 2. We substituted 1 for W sub 1. So 1 comma 2 is one vector that's perpendicular to W, or to V, sorry. So now to find the set of all vectors, we want to write this in set notation, set builder notation. This can be written as the set of all vectors CW, or no, C times the ordered pair of 1, 2, where C belongs to the set of real numbers. It's kind of messy, but
Oh, in the solution thing, you just put it as C2C.
yeah, I just realized that. Let's see if I can make it cleaner. This is what you want your answers to look like. This is called set builder notation for those of you who aren't CS majors. I'm not sure if they require us to write our answers like this. Does anyone remember what they said?
I don't remember what they say, but on the notes is written like that.
Yeah.
Uh,
So sure.
Okay, yeah, it's probably a good idea to write your answers like this. There isn't much to it. Just write an example vector. You need this vertical bar, and then make sure to say what set your variables belong to. Which for our purposes is probably a set of all real numbers.
So what do those values mean in the context of the question?
Okay, what this means is the solution set. So W will be in the form C, comma 2C for all real numbers C. In other words, the vector all vectors in the form C, comma 2C will be perpendicular to the vector 2, -1. Yes. Yeah, we found one perpendicular vector, and to find all the others, we just multiply this by any scalar. Does that make sense?
Yeah, no, I got it.
Cool. Should we do 6B and 6C? They're a little bit more complicated, but it doesn't look too bad to me. I'm not sure if we're actually required to know this. I don't remember doing a problem like this. Should I skip it or not? I'll skip it. Let's do 7. 7 looks like it's probably important. Okay. Seven A says find the angle cos theta between the vectors v equals 1 root 3 and w equals 1 0. The way we solve this is v dot w equals the magnitudes times the cosine of the angles, which is the magnitude of vector 1 would be 1 plus 3, which is 4. Okay, square root of 1 plus 3, which is square root of 4, which is 2. And the magnitude of vector w is 1 times cosine theta. And v dot w would just be 1 times 1, which is 1, plus root 3 times 0, which is 0. So 1 equals 2 times 1 times 2 times 1 times cosine theta, which means cosine theta equals 1/2, which means theta equals pi over, it means theta equals pi over 3. Am I correct?
Yeah, that's what I got. Yeah.
Okay. I mean, I can check my answer. I'd rather not. Anyone have any questions on that one?
How did you get the 1/2 for cosine theta?
Yeah. So I have the dot product of these two vectors gives me 1. I have 2. I have 1. I have cosine theta, right? So 1 equals 2 times 1 times cosine theta. Divide both sides by 2. Cosine theta equals 1/2.
Okay.
Okay. Let's do B. I feel like C and D are repetitive. Let's just do B. B says V equals 2, 2, negative 1.
Yes.
And W equals
2, negative 1, 2.
Okay. Okay. Now you want to set the dot product equal to the magnitudes times this cosine theta. So the magnitude will be 2. Well, the dot product will be 2 times 2 plus 2 times -1 plus 2 times -1, which means 4 plus, or 4 minus 2 equals. Now we want to find the magnitudes of these two vectors. So that will be 2 squared plus 2 squared plus -1 squared, which is 4 plus 4 plus 1, which is 8 plus 1, which is 9. Square root of 9 will be 3. So the magnitude of this vector is 3. 3 times this. The magnitude of this vector is also 3 because it has the same components except in a different order. So 3 times cosine theta. Now this is equal to 0. 0 equals 9 cosine theta, which means, and if cosine theta equals 9, then theta equals 90 degrees, or theta equals pi over 2. Anyone have any questions on that one?
Looks good, seems.
Okay. Let's do one more.
We're talking about for this section in general, or
Yeah, let's do one more from this section.
can we
and
do
then-
I
let's call
have
it
a request. Can we do one of the ones with the like the Schwartz inequality stuff?
What was that?
Ones with like the Schwartz inequality, the triangle qualities. I think 29
Okay.
is one of those.
29. Yeah, I mean, without looking at the solution. Yeah.
Yeah, I wasn't sure if we had to like remember the Schwartz inequality thing.
I think
Funny.
we, because I was looking at the other exams from last semester, and they have some.
Yeah, it's funny. The textbook has the words recommended next to it, so I think it's important.
Yeah.
Okay. The problem states if vector v has a magnitude of 5 and vector w has a magnitude of 3, what are the smallest and largest possible values of the difference between v and w? And what are the smallest and largest possible values of v times w? Okay. Right. Yeah. I mean, usually largest and smallest possible values should indicate inequality. In inequality, I mean, for me, the word inequality now reminds me of Schwartz and triangle inequalities. Okay. Now let's talk about v minus w. The v minus w, the magnitude of v minus w is I don't remember the triangle inequality now. Let me go back to. I'm in the textbook right now. Let me find it.
So it depends on the on the if you're adding it or using the product. So it's like the magnitude gets moved from like the entire thing to just the individual components. So for like the subtraction one, I think it's the magnitude of v plus the magnitude of w is going to be greater than or equal to the magnitude of both.
Okay. This. Okay. What's the difference between the sum and difference inequalities? Is there a difference? Because v plus w is the same as plus, or v minus w is the same as v plus negative w.
I think they should be the same. So
Okay. Yeah, then, okay. Yeah, less than or equal to magnitude of v plus the magnitude of negative w.
yeah, I think that's
Okay. Which means the magnitude of v minus w is less than or equal to, well, the magnitude of v is 3, right? No, it's 5. 5, and it's if w has a magnitude of 3, negative w must also have a magnitude of 3.
Mhm. So is it 2 less than or equal to 8?
I don't think it's that easy.
Yeah, because it says so. That's because it's asking largest and smallest value.
Right. Maybe the smallest value is 0.
Oh, in the solutions it says it doesn't have the negative w.
Oh, what does it say?
It says the magnitude of v plus the magnitude of w.
Oh, but the negative w is in the absolute, or in the magnitude equation.
Oh
In the
yeah, and the
inequality.
other one.
Maximum's 8. Minimum has to be 2, right? 2. Yeah. So it's between 2 and negative, and 2 and 8.
2 and 8. Okay.
Yeah. Is this all it means? Is it just a plus or minus? Or not?
No, I think it's just 8.
The maximum is 8, but the minimum is
It's just 2.
2. I think the way you find that is just by taking plus or minus. I think the extreme magnitudes are the magnitude of v plus or minus the magnitude of w. And then the magnitude can be, the actual magnitude can be anywhere between the two extrema. Let's do the dot product. v dot w can be anywhere between 0 and 5. Or no, 0 and 15, right? Because worst case scenario, the two vectors are perpendicular. If they're perpendicular, then their dot product will be 0. If they're parallel and facing the same direction, the dot product will be just the magnitudes of each other multiplied together. I think that can be proven using unit vectors. Yeah, I think it can.
You said negative 15 and 15, because I think
Oh,
it does
negative
like
15.
the absolute value.
Oh, yeah, that makes sense. That does make sense. Okay. Yeah. V dot W. Or wait, it's a scalar, so you don't need magnitudes. V dot product of V and W is between open interval or close interval negative 15 and 15. Because 15 is just 5 times 3. Does this make sense? I feel like I've explained this terribly.
Sorry, I kind of zoned out for a second. But you got the negative 15 from the absolute value, right? Is that how you like?
Well, I don't see an absolute value here actually.
Well, absolute value is from the inequality itself, the Schwartz inequality.
Oh. Yeah. Because the Schwartz inequality states that the absolute value of the dot product is between, or is less than or equal to the product of the magnitudes, which means the absolute value. If you take out the absolute value, it'll be the dot product is between the negative of the product of the magnitudes and the positive and the actual product of the magnitudes.
Okay, cool.
Yeah, that's where the negative sign would come from. Okay. Is there another problem anyone wants to do?
Maybe the last one? But 31.
31. Okay, we're given two vectors. What is it saying? Okay. How do you want to do this? Do you want to actually select numbers? Or do you want to show it in general? Go for the
We're
general case. Can't be that hard. So we're given v equals xyz. And w equals zxy. Now we want to find the angle between these vectors. So the angle will be, or the cosine of the angle will be, or no, sorry. the dot product of these two vectors will be equal to the product of the magnitudes times cosine theta. So the dot product will be xz plus xy plus yz. And the magnitude of this vector will be square root of x squared plus y squared plus z squared. Times the magnitude of this vector, which also happens to be the same. So which means we get to take out this the square root. So now we get to multiply this by cosine theta. And now cosine theta is this divided by this. So cosine theta equals xz plus xy plus yz divided by x squared plus y squared z squared. I've done this problem in a problem section before. I don't remember how to do this. Does anyone know how to do this? Yeah. I'm not sure. Oh, we want to find v dot w divided by wait, what? Okay. This is expanding this sum of squares and subtracting. Oh, because this is I think this will come about as a result of expanding these sum of squares. Yeah. They're not going to ask us a question like that on the exam.
Yeah, this one's a challenge, so they're not gonna include that.
Okay. Does anyone have any questions? What time should we do tomorrow? 6 tomorrow? Oh, someone sent the solutions for 31 from their TA.
Yeah. I was hoping we could do 8, but if 6 is fine with everyone, I'll do 6.
Yeah, I mean 6 works fine for me tomorrow and the day after. Maybe also Monday, but Tuesday 6 will not work for me. But we can plan ahead later on. Yeah.
We're just doing 2 sections at a time, right?
Yeah, we might do only one tomorrow, or depending on how dense the next one is.
Hey Vishnu, how many what'd you guys go over today?
We have 1.1 and 1.2.
Okay. And what were those questions? Where'd you guys find those questions?
Textbook.
Okay. All right.
Remember our discrete math sessions?
Yeah, I do. Dude, I thought this one was at 8, so
Yeah, it originally
I didn't
was.
see the. Yeah, I didn't see the change.
Okay, let's do same time tomorrow.
Yep. You have a YouTube channel, Google Drive. You can probably use that.
You can also just post it in the Discord.
Yeah.
Yeah, it's a limit. So I would say YouTube is
Right.
probably more convenient because they can also skip around easily.
All right. Is anyone interested in that?
I can make. I'll make that later.
I
Oh,
mean,
Walrus. There's a place called walrus.tv. You can if you can make your video into MP4, you can post the link in there.
does the stuff stay there permanently?
You gotta as long as the room's up, but
No, it'll go away. You don't want it.
Yeah. Probably YouTube.
Okay.
Probably YouTube. I would say. Even if
Yeah.
you want, if you don't want people to see it, you can just make it private, like just unlisted, so that way it doesn't, get in recommended. But you can just make it a playlist, and we can just click back, so we don't have to have multiple links. We just have a link to a playlist. Sure. I think I have an extra YouTube account. Yeah, I'll just wait. What's your username? Yeah, just message me and I'll post it. Mm-hmm.
Yeah, great.
You too.
Ariel, thank you.
See you guys later.
Thank you.
Yep.